Good afternoon, everyone, and welcome to Algorithms and Data Structures today. We'll start with a quick revision of what we did last week. Last week, we generalized some of the concepts we had seen before around systems. So we looked into quantum theory, we generalized states, we looked into superpositions and discussed in detail how we can build such superpositions, which are essentially just linear combinations, but we work with complex linear algebra. We looked at a few examples. We saw how we can use the bra-ket notation. So we use a ket for a column vector, and the bra is just the adjoint of the ket. And we saw some operations around cats, but eventually these are just vectors. And we also saw how we can normalize states. And we looked at a few other things, but I also asked you if you want to learn more about the physical underlying concepts. You can read about the Stern-Gerlach experiment on your own and spin. We then saw the bra from the bra-ket notation, and we started to calculate transition amplitudes, and we also saw a physical interpretation of what the inner product actually means with regard to the transition amplitudes. Then we looked a bit more into the orthonormal basis of states. As of today, we will look into qubits. All of this will become much simpler. Yet we generalized these concepts to get the bigger picture. We briefly looked into observables and measuring, but this will become much simpler for qubits as of today. And then we discussed in detail dynamics, and we saw what or how we can do this in terms of matrices, and we saw why unitary matrices are key, so we can actually undo certain dynamics. Then we assembled quantum systems, and we saw how we can then interpret superpositions of these basic states or two basic states coming from these two systems we are assembling. We looked at a few examples also with regards to the probability of observing the particles at specific positions in the individual states after measurement. And we discussed entanglement, and we saw that these entangled states, they cannot be formed by the tensor product of the two individual systems. And that's something quite interesting. And these entangled states, they will play a bigger role in some algorithms, but also possibly in some of your seminar presentations. Now, before we start looking into architecture, I have just mentioned the seminar presentations, and I'm very happy that 90 students already have signed up for the examination, which opened a few days ago, so you can sign up. I don't know what the deadline is. I think it's usually a 2-week window or something. In case you got any questions about signing up for the exam with regards to the process in Primus, please ask the Center for Studies, because I don't have access. I only get to see the numbers, and 90 students have signed up. However, I have also received a few questions today that I will just answer here now for everyone, because some students may have the same question. So I said from the beginning that these seminar presentations would be groups of 2 to 3 students. I received a few emails from students writing they are 2, if that's fine. Yes, 2 to 3 students means 2 students or 3 students. So please avoid spamming with obvious things that are already written here in the slide deck. And I had also told you that the seminar presentations will only take place on campus. That's why I was a bit surprised to receive another email today from someone asking for an exception because he or she won't be in Germany when we have the presentations in January. You're supposed to be here during term time, and we do these presentations after the term has resumed after the new year, and you're supposed to be back in January anyway from your home country, because Courses will wrap up and we'll have the written examinations as of end of January. So you're supposed to be back mid of January, and there won't be any exceptions. And in a few weeks' time, you need to sign up for these seminar presentations. I had sent a round mail in iLearn about this, for which you saw the deadlines. You cannot sign up yet for the topic. I've only sent you the deadlines already. So you're aware of them, but you'll only be able to sign up for a concrete topic once we have actually finished the content of this lecture. And now we have finished 4 chapters: the introduction, the math foundations. We've looked into systems, including quantum systems. We formalized quantum theory. And now we actually start with computing. And today we will look into architecture. We will see bits and qubits. We will probably not finish the whole chapter today because it's quite lengthy, but we will first of all see how we can describe qubits with our new scheme. We will also see bits just as a comparison. And then from classic binary logic, classical gates and or not, we will describe them with our mechanisms we have established so far, and we will build binary circuits. And once we have seen this, we will see that it's actually not that different to build quantum circuits, because we will introduce reversible gates and so-called quantum gates. So reversible gates are one step towards quantum gates. And since we have already then seen the mechanisms for classical gates and how to build circuits, you will see it's not very different for the quantum ones, yet there are different operations. And then there are a few selected further topics. We will look into architecture this week, possibly next week as well. And I also want you to read a chapter for next week. I had also informed you about this in iLearn. And there's a paper called The Limits of Quantum that was published by Scott Aronson in the Scientific American in 2008. So even though this was 17 years ago, the theoretical limitations of quantum computers, they are set. All that has evolved, all that has evolved in these 17 years is that we now have quantum computers available, but the theory is obviously the same, at least also with regards to the theoretical limitations. And I want you to read this until next week, because we'll discuss it next week. There's first a bit of a revision of what quantum computing is about. And then you will see actually what classical computers can do and cannot do, and which problems can be addressed by a quantum computer. If you're from computer science, you're familiar with the classes of P and NP complete. If you're not, all of this will be explained here in this book chapter, and you will see what the limitations of quantum computers are, and possibly if there could be something more evolved, something more sophisticated than a quantum computer in the future, but that is more like speculative. What is really key of this chapter is this figure here, but in order to understand it, you need to read the pages before. So please do this, because I want to discuss this chapter with you next week. And so next week we finish architecture, because I don't think we'll finish it today. And we will look into the theoretical foundations of computer science. And then in the coming weeks, we will discuss selected algorithms, concrete quantum computers, and programming, as well as applications. And once we have finished all of this, I will also say more about the seminar presentations, and you can sign up for a concrete topic. But in terms of the slides, what you have noticed is we've already finished half of the slides, because we've had 4 extended lectures already, and the lecture part is only about half of the term, so you have enough time to also think about or prepare your seminar presentations. And we will also have some guest lectures in the coming weeks. So in a classical computer, you deal with bits, and a bit is a fundamental unit in a classic computer, and it's from a two-dimensional classical system. And there are lots of interpretations what a bit can actually mean. So one can say a bit is a way of denoting true or false. If you see it from a logical perspective, a bit could also mean that some transistor is turned on or off, or if there's actually electricity traveling through a circuit or not, or at high or low voltage, whatever. So there are lots of interpretations what a bit can actually mean. And what we will do now is we will formalize this and we will try to describe how we can represent a bit from our framework we have seen so far. And once we have done this, uh, and once we have formalized a bit, we can formalize a qubit, and then we can start using all of this theory we have built so far for computations. So we want to represent bits and qubits. And what we need for this are two fundamental states. And we've seen states last week, and you've seen the ket notation. So today we will introduce two very fundamental vectors that or states that we keep using throughout this course. One is 0 ket. So 0 ket. And 0 ket is just a vector. I don't know where this 0 came from. And 0 ket is a vector, a 2 times 1 matrix, or a vector with two entries, where the first entry is a 1 and then a 0. And we can add some comments to this, what it actually means. So I'm just putting the comments here in blue. The first entry, which is 1, represents a 0, and the next entry, that is 0, represents a 1. So this would be from a logical perspective, would be a false, because what I have set is a 1 for the 0 or the false. So the 0 ket represents a 0. And like this, I can also define, and in blue, it's only a comment. So it's only shows you what it means, but it's not an entry of the vector. And as we have a 0 ket, we can have a 1 ket, and we have a 0 and 1. And again, the meaning here is the same. So we have a 1 for the entry that represents a 1. And like this, we can represent a true or an on or a 1 or whatever. Maybe just signal to me that this makes sense to you, that we have introduced a 0 ket and a 1 ket. If you followed last week's lecture, it's just a simplification of what we have done last week. Now, when we look at a classical bit, a bit is either in 0 ket or 1 ket. And that's what you have always learned in a classical logic world, because either electricity is running through or it's off. Either it's true or false. Either some switch is on or it's off. But in a quantum world, we need more than just yes or no. In the quantum world, we need a superposition. So our qubits, they will be simultaneously in 0 and 1 with a certain position. And so we can think about what a qubit is. Well, focus now is a qubit. And a qubit is a quantum bit. And this qubit sometimes maybe also be written just Q bit without the U, but it's the same, just shorter way how to write it. This is a unit of information that we use in our quantum computers or in quantum computing. And we also describe this with 2 dimensions. And concretely, a qubit could be thought of the following. A qubit could be thought about that I have 2 entries, but these entries are complex numbers, Z0 and C1. And I'm adding again the commons for the 0 and 1. So I'm in here in 0 and 1 with a certain proportion, and that proportion is, for this we use a complex amplitude, Z0, and another complex amplitude, C1. And we assume this is normalized. And as you remember, last week when we defined states, in general, there was also a constraint of how the modulus squared needs to add up. We said the modulus squared of all the entries needs to add up to 1 so that we have a valid quantum state. And I told you last week we would see all of this last week from a very generic perspective. And this time we just simplify this to 0 and 1. But it helped that last week we discussed this from a much more extended and generic perspective. So we have a constraint, and the constraint is that the complex amplitude C0, its modulus squared, and the modulus squared of the other complex amplitude C1 must add up to 1. It's just two entries this time. And last week we looked at what C0 and C1 modulus squared mean. And as you remember, we said that after measuring the qubit, or after measuring a complex state, this time it's just a qubit. So the C0 modulus squared, this would mean after we measure the qubit, it will be found in state 0 ket. And 0 ket is up here. While the C1 modulus squared, that would be the probability of finding our qubit in state 1 ket after measurement. But always after measurement, because then we have the collapsing. And eventually, your classical bit is just a special type of a qubit. Because a classical bit would be just either in the one or the other. So you would have a 1 and the other one would just be 0, the other amplitude. So we can see the classical bit is just a special type of a qubit. And what I wrote here in green, and this can be written in many ways. And you will see also in the literature lots of ways how to write this. And I just want to show you a lot of equivalent representations because you will see them a lot in the literature and also in the course. So if I have my qubit where I have these complex amplitudes Z0 and C1, which are complex numbers, I could rewrite this just as a linear combination. I could say it's C0 times 1, 0 plus C1 times 0, 1. Like this. In blue, this would represent the C0, and in orange, this would represent the C1 as the second entry. Are you with me that these two representations are just the same? Just mean exactly the same, maybe confirm with some reactions, which looks good. And we could rewrite this again. We could say Z0 and Z1. And here I could just write my 0 ket and here a 1 ket, which we had introduced up there. So because what I had here in green is just the 0 ket, and what I had in red is just the 1 ket. So all of this just means exactly the same. But we assume that it's normalized. And if you could think about, we have a qubit, something like V, which has two entries, 5 plus 3i, 6i. Is this qubit normalized? Is this a valid qubit? Maybe just vote if this is something you think is valid or invalid. We got just one vote, maybe a few more votes. Green one would mean it's normalized, and red one would mean it's not normalized. Please, now we got a few more, and you all agree that this is not normalized. And as you remember, we could normalize. So we could think about the norm of this. And the norm would be concretely square root of 70. We've seen last week how we can calculate this. So if, and we won't do this now again, you've seen this plenty of times. So we could think about, we can normalize V. So we divide V by its norm. And that would mean that the first entry gets normalized or gets divided by the normalizer. So divided by the square root of 70. And the next entry as well. And we can, again, rewrite this just with the notation before. So we could just say this is 5 plus 3i divided by the square root of 70 times a 0 ket plus 6i divided by the square root of 70 times 1 ket. So this would be just a different way how we can write down the normalized qubit. And again, these probabilities here, they mean something. So the first one would mean that we would take its modulus squared. So modulus squared, we would get actually 34 divided by 70 if I take this complex number and calculate its modulus squared. If I take the other one's modulus squared, I would get 36 divided by 70. And this means if I measure this qubit, so after measurement, I would have a 34 divided by 70 chance the qubit is found in 0 ket, so it would be 0. And there would be a 36 divided by 70 chance the qubit would be found in a 1 after measurement. So this is what this means, and that's why we spent quite some time last week thinking about these probabilities after measurement, and now we see what it actually means from a computational perspective. Then when it comes to the measurement, all I'm showing you is also written neatly in the slides, but we just visualize it here. So if I have my qubit, Z0 and C1, there are two ways. So when I measure it, it would be either observed in the 1-0, which is the 1 ket, and we use this weekly line for measurements, or in 0-1, which is the 1 ket, and the measurement probabilities here are just C0 modulus squared and C1 modulus squared. What another measurement probability is the probabilities of finding the particle in either 1-0 or 0-1 after measurement, because the measurement leads to a collapsing of the quantum state. So so it's eventually just a simplification of what we did last week for a lengthy time. And we've seen there are these different notations here. And this is something you have to get comfortable to very quickly in this course, and also spend some time on revision, because we will use these different notations all the time and they all mean the same. And later they will look even more complex when we have multiple qubits, when we, for example, entangle 2 qubits. We've seen entanglement last week. So today or next week, whenever, we will start entangling qubits. And then this looks even more complex. So there's another example here, just to rewrite this in many different ways. And you need to become comfortable with this. Imagine I have a qubit 1, 1. Is this a valid qubit 1, 1? Maybe green sticker if you think it's a valid one, or red sticker if you think it's an invalid one. Now, since all the answers are correct, it's not valid. I'm not asking you for an explanation because we still need to normalize because it's not normalized. So this can be rewritten in many ways. So we've put a constant factor in front of the vector. We could move this factor inside, multiply it with every element. So we could have a 1 divided by the square root of 2, the 1 divided by the square root of 2. This could be written also using the cats. So a 1 divided by square root of 2 times 0 cat plus 1 divided by square root of 2 times 1 cat. We could move this factor 1 divided by square root out because both the 0 cat and 1 cat, they have the same factor. So we could move this out and say 1 divided by square root of 2 times 0 cat plus 1 cat, just the same. And then there is one notation that is quite common, that we would write this as a fraction because we have the 0 cat and 1 cat as the numerator and the square root of 2 as the denominator. So this would be 0 cat plus 1 cat, and the denominator is the square root of 2. And this is in fact a very common qubit that you will see quite often in this course, because it's a so-called equal superposition, because I have these equal probability amplitudes. And they are complex numbers, but here we only have a real component. And this is in fact a qubit we would, or a state we would often start with in a quantum computer when we create first a superposition, and then we use more advanced gates for manipulations. Are you all okay with these steps? Maybe just signal me what I have just shown you, that you're okay with these steps. Now, quickly wait for more responses. So everyone looks fine. And there is another equal superposition that you would also see quite often. It doesn't look that different, in fact. It's a 1 divided the square root of 2, and then we have a 1 and a minus 1. And this one, again, just what we have done before, we can use lots of ways how to rewrite this. So it's 1 divided by square root of 2 as the first element, and the other one minus 1 divided by the square root of 2. We can again rewrite this as a 1 divided by the square root of 2 times 0 cat, and then we have this minus here, minus 1 divided by the square root of 2 times 1 cat, and then we can again take this factor, so 1 divided by the square root of 2, and we can multiply this with the difference of 0 cat and 1 cat. So this minus here in blue is moved in there. And we can rewrite this again as 0 cat minus a 1 cat divided by the square root of 2. So this would be another equal superposition, because it's an equal superposition even though I have a minus here, but eventually for these probabilities after measurement, I care about the modulus squared, So the negative one here doesn't matter. So after we have developed this on the slide deck, on the whiteboard, we will switch for a little bit to the slides. I have now skipped in the slides, we've seen already the 0 cat, the 1 cat, how we represent qubits, the measurement, these different notations, one example here of normalizing, and further notations that we have just seen. So it's all in the slides, well formatted. Now, we've seen this now from a purely mathematical perspective. One question is how all of this could be implemented in a concrete computer. In a few chapters, we will look at concrete quantum computers, and we will see different implementations. We could think about that we use an electron that might be in one of two different orbits around the nucleus of an atom. We might see that a photon could be in one of two polarized states. We could also think about other subatomic particles that might have one of two spin directions. We've seen spins last week briefly. And there are lots of other ways, also with ion traps and other things, how a quantum computer could be implemented concretely in a piece of hardware so that we represent qubits in some physical way. We will see, this is just an example, we will see other ways how to represent this in a real quantum computer in a few chapters. And every year, since you have started looking for seminar topics, every year there are also multiple seminar presentations about specific quantum computer architectures, specific vendors. There are lots of different vendors now, and how they actually build quantum computers in order to represent qubits. So it could be one hint also with regards to the seminar. Now, as we have looked at qubits and bits, you know also what a byte is in classical computing. A byte, we just have 8 bits combined to have a byte. And like this, like we have a byte composed of 8 bits, we could have a so-called qbyte represented by 8 qubits. But this will look a little bit different. So when we have a qbyte, something quite interesting will appear. If I have 8 bits, so 8 classic bits combined, I have 1 byte. And each bit is either 0 or 1. So I have one state that has 8 entries, which are each either 0 or 1. Now, with a qbyte, something different will happen. I have 8 qubits, but for each qubit, I have my amplitudes for 0 cat and 1 cat. So something that will happen with a qbyte is, with a qbyte, I can represent 2 to the power of 8 many states at the same time. Because in each qubit, I'm partially in 0 and partially in 1. So I'm 0 and 1 at the same time. And then 2 to the power of 8 is 256. And I can represent that many states at a time with 1 qbyte. So this leads to massive parallelism because I not only have one state of 8 entries, but my qbyte is in parallel in 256 states. And then if I manipulate my qbyte, I could manipulate 256 states in parallel. And this will lead to a massive speed up because of that superposition. So I would represent with a qbyte, so an 8 qubit system, 256 states at a time from 0, 1 to 0, 1 up to, C0, Z1 up to Z255, so 256 entries. Down here or to the left, I only have a comment, and a comment means that, and we will see probably this notation later in greater detail, what these comments mean with multiple qubits. But this helps me to enumerate them and to look at each qubit at a time, at which one I look at. We will see this later. But these complex entries, the sum of their modulus squared needs to add up to 1. And if you're confused by this notation here, you will see it in a moment when we start building circuits. Because this is eventually one quantum state, and we will see later how we can build such qubits or how we can combine multiple qubits. Eventually, we aggregate 8 qubits. You've seen aggregation before, and here we aggregate our qubits. So eventually, we will have a state in this aggregate or composite system, and then all these CIs, their modulus squared, needs to sum up to 1. We'll see this later how to build that. And nowadays, we have very simple quantum computers. They are not too powerful yet. They are still very limited in terms of the qubits they got. But something you could think about is if I can actually simulate a quantum computer in a classical computer. And I'm able to do this, but only to a very limited amount. Because you've seen we already have 8 qubits combined. And in order to express that system, I would need 256 complex numbers. Now, you could imagine, say, I'm not taking 8 qubits as a qubit, but I'm taking 64 qubits, so a 64 qubit register. In order to represent this, I would need 2 to the power of 64, which is a very large number, and I would need that many complex numbers just to represent such a quantum system and then to simulate it. And this is beyond our current storage capability. And even if we had a computer for this, we could just double this to a 128. And then 128 would be 2 to the power of 128 would be a way bigger number than this number here. And then we also wouldn't be able to simulate it. So simulating quantum systems in a traditional computer, even in a high performance system, is extremely limited because I just run out of space and processing power to manage that many complex numbers. You can simulate small systems, but not very large ones. And that's why we need quantum computers to actually represent this efficiently, and also not just to represent such systems, but also to run such tasks extremely fast, because quantum computers not only would allow us to represent such larger quantum systems, but also to take advantage of the superposition to run such computations much faster, provided we have an algorithm that could do this, and provided we have a quantum computer that could run this, but we want to get massive speedups. And with a simulation, we don't get speedups. Actually, it will run much slower because it's a simulation, and the simulation is also extremely limited in terms of what I could actually run, even in a high performance computer. So, are you all okay up to here? Maybe a few more responses, please. Now that we have looked at individual qubits, we will look at more qubits and how we can actually aggregate them. And do you remember which mathematical operation we used for aggregating quantum systems or for aggregating systems in general? Maybe tell us in the chat. So this is also a revision whether you have followed the last 2 weeks. Tell us in the chat which operation we use to aggregate systems or to build composite systems. Got the right answer now, a tensor product. So we can write a qubit pair using a tensor product. For example, I have one qubit. We're starting with simple ones. One qubit is just in zero, so a zero cat, and the other qubit is a one cat. And the way I can write this is to use this tensor product, and we can write this just in a somewhat shorter way. As you will see very often in this course, I just write the 0 and 1 and like this. These notations here mean the same. The second one is just much shorter, and there are lots of other notations for this one to keep it even simpler. So some people write, for example, a 0 cat and a 1 cat. Some people write a 0, comma 1 cat, or some people just write a 0, 1 cat. All of this means exactly the same. It means I have actually a composite system of where the first system is in the 0 and the other system is in the 1. So the first qubit, the first system is a 0 and the other qubit is a 1. And I could write this again also as a vector if I wish. And this vector would have four entries because we have a two entry system and a two entry system or two position system and a two position system. So the aggregate system would be four positions. And I'm adding some comments. So the first entry would represent 0, 0. The next one 0, 1, 1, 0, and 1, 1. Where this one here means first qubit, and this would be the second qubit. It's just a notation, and these comments, they actually help so we know how we actually put these qubits into order. Later we will visualize circuits and we'll see some tricks for that. But now I can put four entries into this vector. What, maybe without looking at the slides, you can think about what the entries of this vector would be to represent this one here, a 0 and a 1, or all the other notations. So what would be the four values I would put in this vector, which is just another notation for all of this? Seems like the screen share terminated. I'm sorry. If this happens again, I don't look at the chat all the time. Also, just ping me and turn on your mic and tell me because it's something I just don't see and something. If the screen share terminates, I have no control over. So always feel free to turn on your mic and tell me directly this happens. So what entries do I need to put into this vector just to describe this? That I have a 0 in the first entry, or in the first qubit, and a 1 in the second qubit. Which four values do I need to put in this vector? If you have an idea of these four entries, just send them to the chat. I haven't seen any responses in that chat yet. If you feel you have an idea what it could be, maybe send me some positive reaction, then I'll wait for you. If you don't see the answer of this, maybe just send a negative reaction so I don't need to wait. So, because with these comments here, all I'm doing is I have one column in the comments for the first qubit and a column for the second qubit. And we said now we have an aggregate system. We've seen aggregate systems last week. We say we have the first qubit in a 0 and the second qubit in the 1. So we put a 1 in here to describe this, and 0 in all the other entries. And that's why the order of these comments here is important. If you flip them, then the vector may look different, but there will be some rules we will follow to see what we put in which order. But here, this would be a 0 because the first one would be a 0 because the only thing that matters is the 0, 1. So we put a 1 in here and the 0 for all the other entries. We'll later see more complex ones, but we are not there yet to build this. And in a few slides, we start building some more sophisticated circuits of multiple qubits, and we'll see that. But actually, we can think about such an example, not how to build it from a circuit, but simply we will take such a qubit. So another example, or we take another 2 qubits, and so first qubit and the other qubit, and I'm putting comments here 0, 0, 0, 1, 1, 0, and 1, 1, just the same comments. And the comments, they don't add any values in the vector, they just add an explanation, or we see what these entries mean. Now, let's say something, we have a superposition, because now we actually have a proper superposition here. So say 1, 0, minus 1, and 1. This is my this is a state of a 2-qubit system. So we have an aggregate system. Is this a valid state? What do you think? Thumbs up, thumbs down, green sticker, red sticker, if you think this is valid or not. So I see disagreements. It's not valid. I need to normalize. Which factor would I need to normalize this? You can set this to the chat what the normalizer would be. So the normalizer, that's correct. It's 1 divided by the square root of 3. We've seen normalization a lot last week. And again, we could rewrite this in many, many different ways. We've done this before for a single qubit. We've seen all these ways how we can rewrite this. And so we can rewrite this here again using different notations. So one way we could rewrite this is something like 1 divided by the square root of 3 times 0, 0 cat, which would this 0, 0 cat would refer to this one. And we have the constant factor, the 1 divided by the square root of 3. Then we have a minus 1 divided by the square root of 3 times 1, 0 cat. We have these entries for here. The minus, don't miss it. Plus, we have a 1 divided by the square root of 3 times 1, 1 cat. And we can use a different color for this, for up to here. Are you okay with that notation now? We've done it for a single qubit. Now we can use it for a qubit pair. Maybe just signal me that you got this notation here. It looks okay now. And again, we can use a fraction to describe this because we can just use the normalizer in the denominator, and in the numerator, we just put 0, 0 cat plus 0, um, 1, 0 cat plus 1, 1 cat. Good. And we can generalize this. So for a two qubit system, so generalization of a two qubit system could always be written like this. So we have a psi cat and we have a 0, 0 cat. We have a 0, 1 cat. We have a 1, 0 cat and a 1, 1 cat. And we add these factors, which are our probability amplitudes, complex ones. So C00, C01, C10, and C11. Now this would be just a more generalized description of our two qubit system. And we can think about another special case, which is the following system: 1, 1 cat plus 0, 0 cat divided by the square root of 2. We could rewrite this as 1 divided by the square root of 2 times 0, 0 cat plus 1 divided by the square root of 2 times 1, 1 cat. And do you have any idea? And there's a question here in the chat. I don't really get your question from the typing. Maybe turn on your mic and refer to the to what I wrote here to actually know what you are.
In the example.
Yeah, now I see it. Next time, just turn on your mic early because it will help everyone if we fix this very quickly. And because I'm unable to check the chat all the time. Yeah, it's correct that this is the minus. It's correct in the slides. So next time, just tell me earlier because everyone will benefit from fixing these typos quickly. So we had a minus here up there. That's correct. And now I have this particular state here. Anyone has an idea what could be happening between these two qubits in this system? It's something we explored last week when we looked at quantum mechanics. Any suggestion? Maybe send this in the chat. What this two qubit system here may represent? Because I have a 1, 1 cat and a 0, 0 cat. I do not have a 0, 1, and I don't have a 1, 0. I'll You can also send some signal, thumbs up, thumbs down if you see what I want or if you don't see it. Orthonormal. Well, we always have an orthonormal basis of the qubits. Here, this would also be an orthonormal basis of this system. We would have this anyway. Also for the one before, we would have an orthonormal basis. In fact, then I'll tell you, these two qubits are entangled. We saw this last week and we said if two qubits, we didn't say qubits, we said two states that are entangled, uh, or two systems that are entangled. And then we said if I have entanglement of these two systems and I measure the first system, then because of entanglement, the other system would also be automatically measured. Is this something you remember from last week? We looked at this and saw there was also this physical experiment of how fast entanglement actually is, or at least some minimum, but we say it happens instantaneously. And this here would actually refer to two qubits that are entangled because I have this 0, 0 and a 1, 1 only. So if I measure the first qubit and it turns out to be in 0, then I know the other qubit must be in 0 as well. And if I measure the first qubit and it turns out to be in 1, then I know that the other one is in 1 as well. And it not just happens with the first and the second qubit, it's a symmetrical relationship. If I measure the second qubit, I would also have automatically measured the first qubit. So as we see, this is one way how we can describe, or in our notation, describe two qubits that are entangled. Now that we have introduced this fundamental terminology, we will go back to our slides briefly. We've done a few slides on the whiteboard, like we've looked at this how to build, how to aggregate systems. We've seen these examples here and in the slides. Minus is correct as it should be. And we've seen this example of entanglement. And now we have finished describing bits and qubits. Now we want to use them for computations. And we start with our classical gates. So you know our classical gates, not and or. And we will describe them now using our vector or matrix notation and use vectors to describe our states. And once we have done this, we can further improve it or extend it for quantum gates. And we want to use first of our classical logic gates because you're familiar with them. And you have learned about these classical logical gates purely from a logical perspective in your first semester when you studied computer science. And this time we will see all of this from a vector matrix notation, so purely from linear algebra, not from a logical perspective. But this will turn out to be very helpful because then we can use all of this for quantum gates. Now, for example, imagine we have some gate, and that gate would have n many inputs, for example, 5 inputs, and like 2 outputs, m many outputs. Then I can represent such a gate by a matrix. Concretely, I could represent the inputs, these n inputs, by a vector which has 2 to the n many entries. So far, it's classic binary values 0 and 1. And I have these m outputs, and I would represent them as 2 to the power of m many entries in a vector. I write here a 2 to the n by 1 matrix, so just one column would be a vector, and 2 to the power of m by 1 matrix would be just another vector. But this is how I describe the inputs and the outputs, and with which matrix can I represent the actual logical gate. It turns out when we multiply a 2 to the power of m by a 2 to the power of n matrix with our 2 to the n by 1 matrix or vector, then what we get is a 2 to the m by 1 matrix. So this is my input, which I multiply from the right with my matrix, and I will get that output because I wanted n inputs and m outputs. And that's why in order to make this happen, when I multiply this vector here from the right, I want to get that output. My matrix needs to have 2 to the power of m many rows and 2 to the n many columns. It's also a motivation here for this, just in symbols. But we will look at some examples and see that this actually works. And we will just formalize our classical binary gates. And once that's done, you'll see it's fairly easy to use all of this for quantum as well. What is the simplest binary gate you remember from your first semester? Really the simplest one possible. We can collect here in the chat. The NOT gate, yes. Well, even simpler, we could have the identity gate, which doesn't change anything, but we assume there is some change. So we want a NOT gate. And the NOT gate, there are different ways how to write this. In Europe, often we have a notation like this for the NOT gate. In the US, some notation like this. Which one are you more which one are you more familiar with, the European notation or the US notation? If maybe the first one you sent, the first one, the Europe notation, you would just send a green reaction. For the US notation, a red one. So mainly the US one is something you have seen. Fine. We first now for each gate we look at how it works from a logic way. And I have an input, say the input in and out. I have a 0 input, I have a 1 output, I have a 1 input, I have a 0 output. And maybe we write this in a different way. So we have, say, an input X and an output Y. So we just invert the input. And it turns out we can describe this as a matrix. And the NOT matrix will be a 2 times 2 matrix, and we add some commons. So we just use this systems approach we had started a few weeks ago, that we have systems, and we transform some state into a different one. And that's what I want to describe now. And this matrix will be, in fact, quite easy, because what I want is, remember, the columns represent the inputs, the rows, the outputs. We've done this when we formalized systems and started with deterministic systems, then probabilistic ones, and then quantum systems. So the entries will be like this, because what I want is I have a 0, a 1, and I want to turn it into a 0. And if I have a 0 input, I want to turn it into a 1. Are you all okay with this matrix? Maybe send me some reaction. And we can test this now. What I want is I have a NOT matrix and my state is a 0 ket. So far it's just purely binary states, but later we switch to quantum states with different gates. So I have my NOT gate, which is a matrix 0, 1, 1, 0. And my 0 ket is a 1, 0. And then if I have this matrix and multiply the vector from the right, what I will get is just a 0, 1, because I have this 1 here. All of this would lead to 0, and I have this Yeah, and eventually for the second row, I would have a match here. And so this will lead to 0, 1, which is a 1 cat, as you remember. So we could try it just the other way around, that I have a 1 cat and I multiply it with not from the right, and you would see it leads to a 0 cat. But this is something you can test at home. Which other gates do you remember from binary logic gates? There are two more. Let's see if you remember them and send them to the chat. Or and AND, that's correct. So we do the AND gate after we have done the NOT gate. In the US notation, this is often denoted as something like this. The European notation, for example, something like this. And that's the AND gate. And we will look at its logic table, and then we will start building the gate. So for all the gates now, we start with the logic one. So x1 and where's it? X0 and x1. 0, 0, 0, 1, 1, 0, 1, 1. And the AND gate will only be true if both inputs are true. So all the others here are 0. But only when we have a 1, 1 input, we have a 1 coming out. And it turns out we can describe this also as a matrix. So the AND matrix can look something like this. It would be a bigger matrix. It will have two outputs, or two possible outputs, either 0 or 1. But it can have, it has two inputs. So there are four possible basic combinations of the inputs, which is 0, 0, 0, 1, 1, 0, 1, 1. And because we have these two inputs here, so you see 0, so well, let's say underlined in black is the first input, and in green is the other input, because we have two inputs here. And we can try to describe this now as a matrix. And what I want is for these inputs here, only one of them, or both, or say both of them are 0, or only one of them is 0. What I want is that I map this to a 0. And for the input 1, 1, that's the one I want to map to a 1. Remember, columns are for the inputs and the rows are for the outputs. So I put the zeros here. These are not unitary matrices or anything like this. They will come later for quantum gates. And we can have another example. Say we have an and a 1, 1 cat. And that would be something like just writing down this. And remember, the 1, 1 cat would be 0, 0, 0, 1. We've seen this before. So this 1, 1 would refer to here. We need this entry. And now it's your task to multiply this vector from the right with this matrix. And once you have your output or your result, send it to the chat. You can go very, very quick for you to multiply this vector with this matrix. And once you have the output, send it here. This will be denoted by some cat. So it's 0, 1. So we have this 1 here, and it only matches with this. All the other entries are 0. And this would be a 1 cat. which makes sense now. You can try out the four other cases if you wish and see that this is the AND gate. And as there is an AND gate, there's an OR gate. And the OR gate, the European way, it's sometimes written something like this as one example. The US notation is often denoted like this. And in the OR gate, we'll have again x0, x1, and y 0, 0, 0, 1, 1, 0, 1, 1. Then the result is 1 if at least one entry is 1. But if both entries or both inputs are 0, the output will be 0. And we can represent the OR gate also as a matrix. Remember, two outputs 0, 1, and the input 0, 0, 0, 1, 1, 0, and 1, 1. And I want you to think about what this matrix could look like, maybe without looking at the slides, but you can think about how can I map these inputs to the correct outputs. And if you have the four entries of this matrix, you can send it here to the chat. And we got the right answers in the chat because only the 0, 0 would lead to a 0 and the others are all 1. And you could think again about examples. For example, we have some state, like we multiply OR with 1, 0, and then we have 1, 0, 0, 0, 1, 1, 1. And the 1, 0 would be a vector in which the third entry is 1. And if you multiply this, what you would get is a 0, 1, which is the 1 cat, which makes sense because one entry is 1, so this would lead to a 1 cat. So, and now we will start using this approach to build more complex gates. For example, the NAND gate. Who of you remembers what the NAND gate does? If you remember it, send some maybe thumbs up. If you don't remember the NAND gate, thumbs down. So maybe you can turn on your mic and tell us what the NAND gate does or send it in the chat. But if you turn on your mic, it will probably go faster.
It inverts the output of an AND gate.
Yes, correct. Thank you. So I have an AND gate and I invert the output. Now, how can we represent this with our approach? So what we know is in the NAND gate, we first, so this is the first part, and then the second part, we first do an AND and then a NOT on top. So from the logic table would be something like this, 0, 0, 0, 1, 1, 0, 1, 1. And for the AND gate, well, just extend it a little bit. So the AND gate we had before, on both entries need to be need to be 1 for the AND to be 1. And the NAND is just an inverted AND. It would be just the logical inverse. Now we can think about what this would look like as a matrix. We could either try to come up with the matrix on its own, or we can actually build it from a matrix multiplication. Because I have an AND gate, and we've seen this, how we represented dynamics in evolved systems. We said we have first one operation, one matrix, and then another one. And the other one comes to the left. That's what we saw from the dynamics. So we multiply these matrices. First the AND. So first this, and then the NOT. So we multiply the matrix from the left. And we can just take these matrices from before and multiply them. Remember, the NOT matrix was 0, 1, 1, 0. And the AND matrix, and I'm just adding the comments here, 0, 1, 0, 1, and then 0, 0, 0, 1, 1, 0, 1, 1, and 0, 1, just the comments. The AND matrix was this one here. And you're now tasked to multiply these two matrices. And once you have the result of the matrix multiplication, send it here to the chat. It will be a matrix that has 4 columns and 2 rows. And once you have the result of the matrix multiplication, share it with us. And we got the right answer. You know how to do matrix multiplications anyway. And the answer is something like this, which also makes sense from the logic table, because if both inputs are 1, we want a 0 output, and in the other cases where both are 0 or 1 is 1, we want to return a 1. So a few students tried in the chat, and now you see what this matrix multiplication is useful for from a computational perspective, because I have one gate and then another one. And we will now build not just NAND gates, but we build more complex gates. And for this, we will switch back to my slides. So we saw the NOT gate, we saw the AND gate and the OR gate, and we just built this NAND gate. And the order of these operations is very important, that we first do an AND, and after the AND, the NOT. And we can try to generalize some of what we did so far. So we've seen so far, and we've discussed this once, but now it's just a revision. If I have m many inputs and n many outputs, so m many inputs and n many outputs, then the matrix would have 2 to the n many rows, because these are the rows, the outputs, and 2 to the m many inputs. And then we can now try to build more complex circuits. We have just looked at that already from the perspective of the NAND gate, where we said we have one operation, A, where we have m many inputs and n many outputs. And then we have a second operation, B, which has n many inputs and p many outputs. So the second matrix, B, would be represented by 2 to the p many rows and 2 to the n many columns, because these are the inputs and these are the outputs. And what we're doing here is now a matrix multiplication to represent two sequential gates. And we've seen we always multiply the next gate from the left. So B times A, first A, then B. And A is this 2 to the n by 2 to the m many. And B is 2 to the p by 2 to the n many. And then if I multiply this, so I can multiply because this dimension and this dimension, they are equal. The output will be a 2 to the p by 2 to the m matrix. Are you okay with up to here? Maybe send me some signal if you're okay with up to here. Good. Now, as we have built sequential gates, we can also think about parallel gates in our circuit. So we have two parallel gates, A and B, and A has n many inputs, B has m prime many inputs, and n many outputs, and n prime many outputs. And to describe these parallel computations in terms of A and B, we can do something quite neat. We can represent this through the tensor product because these two run in parallel. We've seen the tensor product before to build an aggregate system of two systems. And later, when we come to quantum computing, we will not just think about bit inputs, but qubits inputs, but it's just the same theory as here. And we've seen for this to aggregate systems, we use the tensor product. In fact, what we're doing here is we're aggregating two because we have two parallel ones that we cannot just use a matrix multiplication for, but rather these two systems. Well, it's not really systems in this case because we don't just have a qubit and we or one byte, but many of them. But this is generalized now. For this, we also use the tensor product. So the tensor product of A and B would lead to a matrix that describes all of this. So we can say if A has m many inputs and n many outputs, it's 2 to the n by 2 to the m, and B has m many inputs and n many outputs, it's 2 to the n prime by 2 to the m prime. And eventually the tensor product, we've studied the tensor product quite in detail in this course now, we would get a new matrix, so the tensor product of A and B, and this output or this result of the tensor product would be a new matrix, which we say the one matrix has 2 to the n and the other one 2 to n prime many rows. So we multiply them. That means 2 to the n times 2 to the n prime would be the same as 2 to the power of the sum of n and n prime. And it works the same for the m and m prime many inputs because we have m and m prime, so 2 to the power of m and 2 to the power of m prime. And this would be, if you multiply them, 2 to the power of m plus m prime. So we see this is actually not too difficult. It's just a generalization of what we did the whole time. Now, as we have built a matrix to describe these two parallel gates, something else could be happening, and we'll look at this. Concretely, you will see is, imagine we have a gate A. It has n many inputs and m many outputs. But not all of these outputs go into B. So we see B is here. It's a second operation. And B has P many inputs. So not all M many from A, but P many. And B has Q many outputs. B is the simple case, as from all the material you have seen so far. But P is less than the M many outputs of A. So we still have M minus P many outputs of A. And if we try to describe this circuit, we see that we have A is fairly easy to describe, A as well, but there is parallelism of A and these remaining outputs of A. Even though there is no operation here, we still need to model this parallelism. And the way we can just think about these matrices, so A is a 2 to the power of m by 2 to the power of n matrix, because n many inputs, n many inputs, m many outputs. B has Q outputs and P inputs. Now, how do we model this? And it turns out, in order to describe this parallelism, I need an identity matrix. Identity matrix is, we have seen, something uh, quite often in this course, and we don't need to draw any gate for the identity matrix because it doesn't change anything. And the identity matrix needs to be of m minus p size. So if m is, for example, we have five outputs, and we have say two outputs going in here, we would need size 3 there. So the way we can describe this is we take B and we take or we first take A, this is the first operation, and then we need this parallelism as the next operation. So from the left we multiply, but we take the tensor product of B and the identity matrix of M minus P. And like this, we can model this parallelism, even though there's no gate. If there was a gate, we would use some other matrix, but since there's no gate, but we still run M minus P in parallel to this, we need to model this with an identity matrix. Otherwise, we have the wrong dimensions and this will not work any longer. So, now we've seen this quite some theory of how to model these circuits, and we will apply this now to a slightly larger example that I will open for you now on the iPad. What I want now as an example is a somewhat more sophisticated circuit, just combining all that we have learned so far. So I will have one bit and a NOT gate. I will have two more bits and an AND gate, and then a NOT gate, sorry, an OR gate for these two, and that's the output. Do you feel confident to model this now with all all the theory we have had so far. Maybe send me a thumbs up if you feel positive about that you would be able to model this, or a thumbs down if you don't feel confident. So one person feels confident. Um, we will start with this part here. We have a not and an and. So we have the not, and it runs in parallel to an and. So we need a tensor product. And then we need to, you don't need to remember these matrices, but I will rather show you what they look like. And we add the proper comments. And then we have the tensor product with the and. And the and we saw before looks like this: 0, 0, 0, 1, 1, 0, 1, 1. And all of these entries were both a 0 or 1 is 0 turned to 0. And in the other case, we have that 1 here. So if we build such a tensor product, it will turn out this is quite a big matrix. So we have, because eventually we will have 2 bits in parallel, so 0, 0, 0, 1, 1, 0, 1, 1. And we have 2 in parallel as the output, but as the input, we have 3 bits as an input. So we need 2 to the power of 3 many columns, so 8 columns. And then this will be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. So we have 8 columns. And obviously, from a logical perspective, you could now try to build this matrix step by step and think about, if the one is true and then it turns false and we have this and. But you don't need to do all this logic. Rather than thinking about the logic for this circuit, you just do the tensor product. The tensor product, eventually, we can think about it. We have 4 of these blocks, so to say. So just draw in some blocks. And it turns out to be fairly easy because I have a 0 here and a 0 there. And then whatever I multiply from the right, I will have a 0. So these entries are all 0 in these blocks. And then I have these green entries in 1. And what would I put into these blocks when there is a 1 in the first matrix? So I have these other blocks here. Well, maybe I don't put them in orange, but rather I would put these blocks in green. So maybe you can tell me in the chat what I would have to put into these blocks now, where in the first matrix I have a 1. Just make the blocks green. And you can send this in the chat or turn on your mic and tell me what we put in here. I haven't received any response yet. Maybe thumbs up if you feel you know what the solution could be, or thumbs down if you don't see the solution, what we put into these blocks. Eventually, it's just the tensor product. And fair enough if you don't see it. Well, you remember from the tensor product, well, one person sees it. So maybe the one who sees this can turn on your mic and tell us, because you're the only one who sent a positive response. But we didn't hear anything from you, so that's fine. So where I have this one here, I would multiply this one with every entry of the second matrix with the tensor product. That means I would just copy the whole matrix into here. So 1, 1, 0, 1, 0, 0, 1. The same here as well. So even though this is just zeros and ones, it doesn't behave different to when we studied the definition of the tensor product and we applied it to build aggregate systems. Here we're also building a composite system. We're aggregating systems, but this time the systems are bits and simply not quantum systems. The quantum bits will come later. But this matrix here now describes this first part that I have put in blue here, because I have 3 inputs, so 8 columns, and 2 outputs, so 4 rows. And what I need next is to think about this OR matrix. We have seen the OR matrix before, and the OR matrix was something like 1, 0, 0, 0, 0, 1, 1. Also putting my commons there, 0 and 1, 0, 0, 0, 1, 1, 0, 1, 1. Now I have this blue part for these two parallel ones, and in red I have this matrix for the OR. What do I need to do next to describe the whole circuit? Because I have the blue part and then the red part. What do I need to calculate? If you see it, maybe thumbs up. If you don't see it, thumbs down. And if you have a thumbs up, maybe you can tell us in the chat what I'm actually hoping to do here. Multiply from the left. Yes. So what I need to calculate now is, so my result would be, I have my not in the tensor product with the and, this was my blue part. And now this was the first part, and then to the right, the next part in the circuit is an OR. That means I multiply from the left, because we always said multiply from the left. It's the next evolution of the system in the dynamics. So what I need to do is I have my OR matrix, and I have the intermediate matrix here in blue, and I need to multiply them. And we can multiply because we see I have 4 entries here and 4 entries here. So I'm multiplying OR from the left. And if I do this, so we can try this out now step by step. So the result matrix will be something like, the result matrix will have 2 outputs, 0 and 1, just from the definitions we saw before. And I have 8 columns here because I have my 3 inputs. So this will stay. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. 100, 101, 110, 111. So this will be the result matrix, and I get it just by multiplying. So I'm putting this here. So this column with this row would be the first result, so element-wise. But these ones don't match, so my output will be a 0. The next one be this column, and my row would also be 0. So I quickly want you to do this matrix multiplication, so multiply or from the left and send me the result. So it's 2 rows and 8 columns, and we've already done 2 entries. So you have 14 more entries or so to think about, but all you need to do are these multiplications. Um, and we have this next column and the next row. So quickly think about what the output could be. This one here, since one already sent an answer, this is really cool. That would be again 0. And we also have a 0 here because the ones just don't match. We have a 0 there. But then we have a 1 up here and a 1 there. So this would actually match. So we have a 1. And if you keep continuing this, the answer, it's also in the slides, would be something like this. Some have already done the matrix multiplication and send it to the chat in the meantime. In the next row would be something like that. And the answers in the chat are correct. So what you see now is when we look at such circuits, we actually don't need to know anything about logic. All we do is we think about this circuit from a linear algebra perspective. And like this, we don't need to think about, oh, we have, a true false and then a true false and what the logic operations are. But actually, all we're doing is we look at that from a linear algebra perspective, and we have matrix multiplications, we have tensor products, and so forth. Do you think this is easier than logic or more difficult? If you think it's more difficult, maybe red reaction. If you think it's easier than logic, the green one. It's there seems to be a majority that this seems to be easier. Well, it's certainly something uncommon I have not seen anywhere before. I started looking into the course book many years ago, but I didn't see that approach to logic gates when I was in my first year. So you cannot build logic gates without knowing about logic, but rather we do this purely from a linear algebra perspective. These are our classical gates, and we have now seen classical gates for classic bits, and we can now evolve by looking into quantum gates. What I want is quantum gates, and so quantum gates, but the quantum gates, they will come in a moment. So first, we actually look into something somewhat simpler, or not simpler, but one step there. We want to look into reversible gates. Reversible gates are operations that I can undo. And from the gates we saw so far, the NOT gate can be undone because I just run yet another NOT gate and then it's undone. But the AND gate is not reversible because reversible would mean I have an output, and from that output I want to infer the input. It's not possible for the IN gate, for the AND gate. It's not possible for the OR gate, and not possible for the NAND gate, and not possible for this circuit here. Because I have an output and I'm unable to reconstruct the input. all quantum gates we want to look at, so quantum gates, all quantum gates that we use have to be reversible. And we first start with a very interesting reversible gate. And later I will tell you why that one is important for quantum computing, but why we don't put it in the chapter about quantum gates, but first in another subchapter about reversible gates. We'll see that later. If we represent our reversible gates and therefore the quantum gates as a matrix, what kind of property do you think what kind of property these matrices would have? Because we've discussed undoing operations and dynamics, and we saw there are matrices with a special property. If we use them, we can undo the dynamics. So what would you guess intuitively if I represent a reversible gate as a matrix? What kind of matrices would that be? And you got it right. They would need to be unitary gates. That's correct, because unitary matrix or unitary matrices, not gates, unitary matrices, and these gates we could undo. The NOT gate we saw is actually also a unitary matrix, by the way, but the AND gate is not reversible. So the matrix of the AND gate is not unitary. It's also not unitary because it's a 2 times 4 matrix, so it anyway cannot be unitary. But the NOT gate, in fact, is represented by a unitary matrix. But we'll see more unitary matrices as we speak. The NOT gate is maybe even not the simplest unitary matrix. The identity matrix is probably the simplest unitary matrix we could think about. And we will introduce now two gates that are reversible, and we will see why they are both so interesting, and they will play a crucial role in quantum computing. The first one is the C NOT gate. Small c for controlled NOT. It's not a NOT gate, but something quite or a bit more sophisticated than a NOT gate. And we will study the controlled NOT gate now. And we start now drawing some circuits, and we look at that from a logic perspective, but all we do is also applicable to qubits once we actually start feeding quantum states in there. But for now, we look at that from a logic perspective. So our controlled NOT gate is something I will visualize. I have two inputs. I have an X cat and a Y cat. These are my inputs. And if I visualize this C NOT gate, my X input will not be affected. The X input will be also just the output. And for the Y, we will get this in red. We get something else out. What is this red symbol from a logic perspective? Do you remember what that one is? It's not a tensor product because it's not rotated. Maybe you can send to the chat what you think this red symbol that I just drew from a logic perspective is. It's a binary operation. It's correct. It's the XOR. Or well, this XOR. Do you all feel okay with XOR or not? then you all feel comfortable. Yet we will still quickly look um, at the logic table. So we're all just on the same page. So we have two inputs, x0 and x1, and then the XOR output 0, 1, 1, 0, 1. And the XOR is 1 if exactly one of the inputs is 1 and the other one is 0. So 1, 1. And if both inputs are 0, the output is 0. If both inputs are 1, the output is 0. So this is the XOR. And in our C NOT gate, just separating this blue from the rest. So we have two inputs, X and Y, or X cat and Y cat. Later, this can also be some quantum state, but for now, we just assume it's classic values. The X doesn't change, and the other out, so X will be the first output, and the second input will be X or Y. So what we can write here is, so the input, black, the input XY gets mapped. So the C NOT gate takes our XY, so XY cat takes this to X and then X or Y. So XY gets taken to X and X or Y. We can think about how we can represent this as a unitary matrix. So our C NOT gate can be a unitary matrix of size 4 times 4, because for now only the logic interpretation matters, the quantum one comes later. So we have 0, 0, 0, 1, 1, 0, 1, 1, if we just assume that X and Y are logic values. And we can think about what this matrix looks like. If I have my input 0, 0, the first 0 just stays where it is, because the first one here, this is the X and this is the Y. And X just stays as it is. And the Y may change or not, but it's the XOR, and 0 X or Y just stays 0. So we put a 1 in here because this 0 doesn't change, so it gets mapped to here. And the Y is the other output. It's a 0, but 0 X or 0 is just 0. So 0, 0 gets mapped to 0, 0. And the 0, 0 doesn't get mapped to anything else. So this column is just the remainder is 0. Now let's think about the next example. This 0 here doesn't change, but the 1 and the 0 XOR is just 1. So also, this doesn't change. 0, 1 gets mapped to 0, 1. So we have the diagonal here, and the other entry is 0. So far, looks like the identity matrix, but now the next part is coming where we see this is not the case. The 1, 0, so the 1 here just stays where it is, but the 0, the second input, we have the XOR, and this XOR of 1 and 0 is 1. And that's why the 1, 0 gets mapped to the 1, 1, which is here. And then the column is 0. The remaining entries is 0. And back here, we can also think about this matrix. This 1 doesn't change. It's the first input, will be the first output. But then we have this is our y, and 1, x or 1 is 0. That's why I put in here. So this is my matrix representing the C NOT gate. Are you all okay with how I developed this matrix, just looking at the logic with the XOR operator? Maybe just signal if you're okay with that. So, seems okay. And this matrix is unitary, as you can look at it and you will very quickly see it's a unitary matrix. So it's a reversible gate. Feel free to test at home if it's really unitary. But now something else that is quite interesting will happen with the C NOT gate. I'll build a more complex circuit. So I have my X and Y as from before. And I put my first C NOT here as before. And we saw X does not change. And the output would be, write the output in blue maybe, X, X or Y. It's what we just did. But now I can put a second C NOT gate there. Now we see obviously at the top the X cat doesn't change. But now the output of this one here will be quite interesting, because before we saw this gets changed to the input from up here, and this input Y, and this becomes X, X or Y. So we take the Y, so the input from here was the Y, with an XOR of the other input X. So what do you think a second C NOT gate would calculate? Because now the input is this one here, X, X or Y, and we have the X here. Maybe you can think about and send in the chat what you think that the second C NOT gate would have as a second output down here, which I have not filled in yet. And you don't need to use the XOR sign, you can just write XOR in your text answer. So think about what this here would calculate. So from blue before we have the X, X or Y. Well, I'll write it just here, X, X or Y. But I still have this X here in green, so another X, X or. And in the comment, we already saw what would be the consequence, but I'll first write it out. So the XY cat gets mapped by the first C naught to X, X or Y. And this gets mapped to X, X or X, X or Y. And now there is some logic that you have learned also in your first year. If you have an X, X or with X, X or Y, we can simplify this. First of all, the XOR is associative. So we can say this is the same as x or x, and then x or y. And what is this part here in blue? X or x. What's that? One person already wrote a little bit about this, but we do a few intermediary steps. You can send this to the chat if you know what's x or x. We can also think about a logic table. XOR is 0 or 1, but 0 XOR 0 is 0 and 1 XOR 1 is 0. So we see that x XOR x is 0. And if I have this 0 x or y, we can also think about this. So I have a y here and a 0 x or y, so 0 or 1. But then a 0 with the 0 of the XOR would be 0, and the 1 with an XOR of 0 is 1. So we see this logic table here doesn't change. So this is eventually just 0. So, sorry, it's just y. So the 0 is a so-called neutral element with the XOR. That means this one up here in red, we can just simplify, and this is the same as just y. That means also here extended, this just gets mapped to x, y. And this is also a consequence, or you can see this from a different perspective, where this C naught matrix is unitary. And if I take its adjoint, which is just the same as the C naught, so C and its adjoint, the C naught and its adjoint is just the same. If I multiply this with each other, so C naught with itself or C naught with the adjoint of C naught, I would just get the identity matrix. So the C naught gate undoes itself. Probably wondering what is this useful for? The C naught gate will be used for in lots of quantum algorithms, the controlled knot. And here we just see, because the matrix is unitary, also from a logical perspective, if you connect the gate to itself, it will undo the operation. And this was a preparation for the next gate, which is the Toffoli gate. And the Toffoli gate, you will later see why this feature that we're able to undo operations is so important. The Toffoli gate is a more complex gate. And in the Toffoli gate, so Toffoli gate, we will have three inputs: X, Y, and Z. Now, this Toffoli gate does not change the first input. It does not change the second input, but the third output will be, I guess I also write this in blue, Z X or X and Y. We can think about what this means from a logical perspective with a table. So we have inputs X, Y, and Z. We will have an X and Y. And we'll start with this. So we look at all the possible values. So what is x and y? Um, when x and y are both 0, so just highlighting the two columns, and only when both are 1, the result will be 1. Otherwise, it's all 0. Are you okay with me up to here? Maybe thumbs up or thumbs down. And now we need our z, x or x and y. I have just computed x and y. And x or z. What we see is I have a 1 and a 0 here. So I put a 1 here, also here, there, and there. And I hope I didn't miss any. And all the others, so I have a 0, 0 in the first one. It's 0, 0, 0, 0, 0, 1, 1. Do you agree with this table up to here? Good. And this table now will be quite helpful to think about the matrix for this Toffoli gate. Since it has 3 inputs and 3 outputs, what do you think is the size of the matrix with which we can represent the Toffoli gate? You can send this in the chat. So it's a certain number by certain number matrix that I need to represent this. So maybe send to the chat what you think the size of the matrix for the Toffoli gate would be. If you don't see it, maybe send a thumbs down, and then I'm fine with that too, because I haven't seen any responses yet. Um, so before we had the C0 gate, which had 2 inputs and 2 outputs, and we always said 2 to the power of that. So 2 to the power of 2, which is 4 times 4. And here we have 3 inputs, 3 outputs, so 2 to the power of 3. So an 8 times 8 matrix that we will build now. So we have 8 rows. And we also have 8 columns. So we can think about what this matrix would look like. We have our 0, 0. What does this get mapped to? So 0, 0, 0. We anyway see that the first two, x and y, don't change. And the last one, which is this one here, may change or not. But we see when z is 0, then the result of this operation here would be 0, 2. So 0, 0, 0 gets mapped to 0, 0, 0. So 1. And then the remaining column are all zeros. What we see is for the next entry, this 1 here, which would be this one, also gets mapped to 1. So we are here in the diagonal, and all the other entries are 0. We can continue this. This one here would be that 0, also stays a 0. So, and I put in all the remaining zeros in the column later. Then we have this 1 here. This one also stays there. And remember that these first entries, 0 and 1, they don't change because x and y just stay as before. Then we have this 0, which is this one here, also stays. So 1, 0, 0 gets mapped to 1, 0, 0. Then we have this 1 here, stays a 1. So this one here, the 1, 0, 1, also stays. And the actual change now comes here. I have this 0, which was this one, becomes a 1. So the 1, 1, 0, what does that get mapped to if the 1, 1 doesn't change and the 0 gets changed to a 1 at the end? So the 1, 1, 0, what does it get mapped to? If you see the answer, send it to the chat. That's the 1, 1, 1. It's down here. And the 1, 1, 1, this 1 here gets flipped to a 0. So I put the 1 in here because my 1, 1, 1 gets changed to a 1, 1, 0. Now we can add the remaining zeros. Just adding all the zeros. And this is the matrix that represents our Toffoli gate. Now, why is this Toffoli gate so interesting? The Toffoli gate is universal. And what this means is if we copy the Toffoli gate, so we have multiple Toffoli gates, and we just use more and more Toffoli gates, we can build any logical gate that we want. We can also do this with an AND, with a NOT, with an or sorry, with a combination, say an AND a NOT, or a NOT and an or the combination of NOT and or. We also have a set of universal gates, or for example, the NAND gate itself is universal from a binary perspective. But the Toffoli gate is universal and it is reversible. So it's universal plus reversible. This universal part here it's universal from a binary perspective. And I told you the Toffoli gate is also a quantum gate. And I told you before I would or I promised you at some point I would tell you why we have a subchapter reversible gates and not directly call that chapter quantum gates, because the Toffoli gate is universal from a logic perspective, from a binary perspective, and it is a quantum gate. I can use it for quantum states, but from a quantum perspective, it's not universal because I need something else, for example, to create superpositions, like we will see such gates or other gates. So the Toffoli gate is a very important gate in a quantum computer, but from a quantum perspective, it's not universal, only universal from a binary perspective. But it is definitely reversible, and we will need reversible computing in quantum computing. And I will show you a few tricks now, what we can do with the Toffoli gate, and we will also see in the remainder of today's lecture why the Toffoli gate needs to be reversible and why reversible computing is so important in quantum computing. Let's try a few tricks with the Toffoli gate and see why it's actually universal from a Boole or logic perspective. So I'll draw another Toffoli gate. Remember, we have X, we have Y, we have Z, and well, the Z is something I put here in red because we will manipulate the Z now. And so this is just the Toffoli gate as we've seen it before. And we said it's X and Y. And we have this XOR with Z. And we'll finish the drawing here. So this is the Toffoli gate as we saw it. But now we said it's universal. I'll just show you a few tricks what you can do, because rather than feeding in Z as a variable, I can just feed in a 0 for the Z. That would also allow me to feed in a 0 here. So 0 XOR X and Y. I have this term. How can I simplify this term? 0 XOR X and Y. It's not too different to what we did before with the C NOT gate. If you have an answer, send it to the chat. If you see the answer, maybe send a thumbs up. If you don't see the answer, what this gate is doing now, maybe a thumbs down. And since someone sent a thumbs up, maybe tell us what this gate is doing. Maybe how I can simplify this term. It's correct. Eventually, I can just remove this neutral element. So what I have built here is an AND gate from the Toffoli gate. It's not just an AND gate, it's a Toffoli gate that I have that calculates the AND for me, and it is reversible. So we have just built a reversible AND gate. Something our classic AND gate was not. I could do lots of other stuff with the Toffoli gate. For example, again, another example here is, so we have X, we have Y, and we have Z. And but I'll just change this and I use other colors to show you what I'm aiming to do. Put this here in red as well. X and Y. And what we want to calculate, as you remember, is we have our Z XOR X and Y. But now I want to change X and Y. I don't want to feed in variables, but rather fixed values. And concretely, I feed in ones. So I put a one cat here. So the one cats also come out. And in here, I'm putting a 1 and a 1, which is just a 1. And what is set XOR 1? What happens to set if I XOR it with a 1? If you have a solution, send this to the chat. I can also provide a helper here. So I have X, so table, and then X, XOR 1, 0 and 1. These are the answers. So what am I doing here? And maybe we just for the wording, we don't call it X, but rather a Z this time. So what am I calculating with set XOR 1 from a logical perspective? If you see the answer, send it to the chat or send me a thumbs up. If you don't see the answer, send it or send a thumbs down. If you see the answer, maybe just send it to the chat, what I'm doing from a logical perspective with that. I'm doing the not, that's correct. So this is just a negation, and I'm just removing this. So I'm using here the Toffoli gate as the not gate. So not gate built from the Toffoli gate. And this Toffoli gate starts to get super interesting now. If I want to have multiple Toffoli gates and I combine them into some bigger structure. So what I want is, so the classic Toffoli gate here we saw has two so-called controlling bits, X and Y, which were these controls here. But I want to have a third controlling bit now. So I want to have a Toffoli gate with three controlling bits. So I'm starting with the first Toffoli gate, X and Y. This is my first Toffoli gate. And what I get out is my X and Y, because this does not change. But my Z is the one for the XOR, as we have seen here. So this was this part. So it turns out if I want to build my Toffoli gate with 3 controlling bits, I have to put a 0 in here. And let's see what is the consequence of that. Um, so 0 XOR X and Y. And we saw that this is the neutral element, this X or 0 X or something. So I can also just remove this and I have an X and Y coming out of here. So I'm just writing this in a neater way. Because a 0 is my neutral element. But this is just now a consequence of what I'm getting here, but rather what I wanted was my third controlling bit. So I'm putting here another Toffoli gate. And I have another Toffoli gate here. I call this Z and W. And eventually this Z will just stay as is. And the question is, what am I calculating down here? I have my W. I'll probably put the W in blue, just that we are all on the same page. I have my W XOR I have this Z and Z. And what else do I have to put in this AND in here? Remember from the classic Toffoli gate, I had X and Y with an AND X or Z. Now I have this W for XOR, I have this Z which goes in here. And how would I complete this term here that I put in red? Do you see what's being fed in from the first Toffoli gate and what would be the impact of this? So it's W XOR and then we have an X and Y and Z. So it's this red part coming in. So now I have built, and we got this here in the chat, which was correct. We have built a Toffoli gate with 3 controlling bits. I only have one problem. And now this will be something that you notice, or maybe you haven't noticed yet, but we're discussing it. I wrote this. So the X and Y. So this would be an output here, X and Y. However, at this blue spot, I had fed in a 0 and I would get something new out, an X and Y. The others have not changed. The X and Y don't change, the Z don't change. Down here, I get the output that I want. But for one bit where I had fed in a 0, I suddenly get out an X and Y. is this something, so we had a zero, now we get in some new output that I actually didn't demand. Is this something that you feel negative about or or okay or neutral? If you feel negative about it, send me a red sticker. If you just think this doesn't matter, send me some other reaction. And maybe some more responses, because so far the number of responses is limited. So one thing we could do in classic binary logic is we could just ignore this and say, well, it doesn't matter. We don't care about it. But if we are in quantum computing, what we create is superpositions. So we need superpositions early on in a quantum algorithm to create parallelism. And then we work with these parallel states in order for a speed up. And if this was now not just classical bits, but qubits, I would create an unnecessary superposition in here. And this will severely complicate my computing and just create superpositions I don't need, which could lead to all sorts of problems when doing quantum computing. And now we're coming to the big answer of how we can fix this. And I've told you from the very beginning of this course that we need unitary matrices. And here comes the solution why we need unitary matrices and reversible computing. Because what I have created here could be an unnecessary superposition. But I can, and it's something I cannot ignore in quantum computing. It will lead to lots of trouble. And maybe in a big algorithm, we need a lot of Toffoli gates or other gates, and we have something like this. And we really don't want that. It's something we cannot just ignore. But there is a surprisingly simple way how to get rid of this problem, and it's by adding a third Toffoli gate. Because the Toffoli gate is reversible. And if you multiply this matrix of the Toffoli gate with itself, it will just lead to the identity matrix. If I add a third Toffoli gate here, what would happen to this area in the red box that I have here? Do you have any guess what would happen to this part that I didn't want if I have a reversible gate? If you have an idea, maybe send me a thumbs up, otherwise thumbs down. And if you think you have the solution, let us know in the chat. I know it's quite late, it's almost 5 p.m. and you've been listening to this for 3 hours. So one person send a thumbs up. Does that person want to tell us either orally, or you can turn on your mic, or you can tell us in the chat what you think could happen here now if I put in the third Toffoli gate? This will just lead to finally that we have a zero again. And that's, I guess, what you also wrote. So everything we have done in here will just vanish. And we have our zero again. And I still leave this box in red because this is probably one of the most important parts of this course as a demonstration why we need unitary matrices, because this third Toffoli gate undoes this, what had happened in here. Undo this one. And eventually we have the zero cat in here. And this is something, and that's why in quantum computing, because if these were now quantum states, we would create unnecessary superpositions. which would severely complicate the further computing and lead to all sorts of problems that you will see when we study quantum computer architectures in greater detail. We want to get rid of that. And that's why we put in here a third Toffoli gate. And it's something you will see in many quantum algorithms when we look at what they are made of. You see there are some operations later, some operation is undone just to prevent things like this, as well as some other effects. Do you feel now you see the big picture? Why I had always emphasized that we need unitary matrices in this course. If you feel you got this big moment now of enlightening, why I always said the unitary matrices are important, send some reaction, some signal. Even though I know it's 5 p.m. and it's the fifth lecture. But now this is the big example why we need unitary matrices. And we will switch back to the slides briefly. So we had skipped a lot of slides, but I had developed all of this on my iPad. So last time we saw this circuit here, this sample circuit, and then we switched to reversible gates. We discussed the C-not gate, and its unitary matrix, two C-not gates, and then the Toffoli gate. And it's universal, very importantly, universal from a logic perspective, but not sufficient as the only gate possible in a quantum computer, because it, for example, cannot create a superposition. So we need something else in a quantum computer plus other gates. Sometimes will make some work far more convenient, but it is, from a logical perspective, universal, and it is reversible. And you can make a reversible computer, so a reversible binary computer, purely from Toffoli gates. But when it comes to quantum, we need to add a little bit on top. We saw the AND gate made with Toffoli gate. We saw the three controlling bits, so the first one and the second one. And this third one is simply to undo what had happened here, that we get still our zero ket. And I felt if I develop this with you on the iPad step by step, and we look at all the logics behind, this will probably help a lot. Um, you can use we've also built a NOT gate from a logical perspective. You can do other things with a Toffoli gate, a so-called fan out. What does a fan out mean? I have a Y input and I want to duplicate the input Y. Um, and you've learned the logics of the Toffoli gate, and I have this Y here, and then I have the output twice. If I put in a 1 in the first controlling, and then for the Z, I put a 0 ket, eventually this will generate a fan out, so duplicate one of the variables. It is very important that this only works for binary bits, or so for binary input, so bits. If you have Y as a qubit, the Toffoli gate will not be able to copy your qubit because there's the no cloning theorem. It's something we see next week, and you're unable to just copy a quantum state. So this works from a binary perspective, but not from a quantum perspective. But we'll see this next week. As there is a Toffoli gate, there is another gate described in the literature, which is also universal. It's a Fredkin gate, and a Fredkin gate it works different to the Toffoli gate, but it's also universal, and you have your X, Y, and Z, and make some changes there. There's also a unitary matrix for the Fredkin gate, and you can use the Fredkin gate to build other gates. But we've done the Toffoli gate, which was already quite tough, I guess, for most of you. If you want to read about the Fredkin gate, feel free to check the book, which covers this in greater detail. But I think the Toffoli gate so far is fine. Now, we have studied reversible gates, and the Toffoli gate we saw will also be used in the quantum world and is represented by a unitary matrix. But we need more gates in the quantum world. And you've seen quite a few quantum gates already. So the Toffoli one can be used in the quantum world, the Fredkin one, the NOT gate. We have seen the classic NOT gate is also a quantum gate because it's represented by a unitary matrix. And if I apply this, the regular NOT gate to a qubit, I would just flip the two amplitudes for Z0 and Z1. I would just flip them. If I apply the NOT gate not only to a bit, but a qubit, the identity matrix is also a quantum gate and the C naught as well. So C naught is something we study today. And next week, we will study more quantum gates. We will actually study the harder MUT gate. It's something we saw briefly already when we introduced unitary matrices. Next week, we'll study it in greater detail. And this is a logic gate, a quantum logic gate that will actually create superpositions. And next week, we will see more possible quantum gates and visualizations of qubits. And we will also look at the no cloning theorem as well as something called mixed states. And we will explore all of this next week. And next week, we will also look at theoretical computer science. And I asked you before already to read the limits of quantum that I mentioned at the beginning of today's lecture. Read this until next week. We'll discuss it next week. And then in 2 weeks, we will look at selected algorithms. So we're doing theoretical computer science first. But first, we will finish next week the architecture chapter, of which we've already done more than half. And next week, we'll look at quantum gates, more quantum gates than the ones we have seen already. And if you have no questions, or if you have any questions, please ask now. I'll just wait a second if there are any questions or not. And with there not being any questions, we are done for today, and I'll see you next week. Please read The Limits of Quantum, spend enough time for revision so you're able to get most out of this lecture next week. Take care and bye bye.